Today we're going to look at finding probability using the normal distribution. A couple terms we need to talk about before we look at the normal curve is mean, which I'm pretty sure you've worked with calculating mean before. Mean is the average of a data set. Usually it's adding up all the values and dividing by how many values are in the data set. Standard deviation is a value that's calculated that shows how spread out the data is around the mean. Data is symmetric when you can have your mean be right exactly in the middle, and then around the mean the data is evenly spread out on both sides. When your data is symmetric, you can use the mean and the standard deviation to get a visual of the spread of data. So the mean gets planted in the middle of a number line, and the standard deviation tells you how to count above the mean or below the mean. So starting at 5 and going above 5 or above the mean, we're going to add 2 to make the next marker, which is a value of 7, and then we add 2 again, which is your standard deviation, to get the next value of 9, and we add 2 again to 9 to get 11. So each time we plant a marker, we're using the standard deviation to add to it to get to the next marker. Usually we go 3 marks above the mean, and then we go 3 marks below. So below 5, we're going to use the standard deviation, but subtract 2 this time to get 3. And then we're going to subtract 2 again to get the next mark, and then subtract 2 again to get the last third mark below the mean. So our standard deviation helps us figure out how spread out we make our markers. So we go every 2 units above, in this case, every 2 units below the mean. When your data is symmetrically spread around the mean, we call that normally distributed data. So when you do know that you have a data set that's normally distributed, we have a special rule called the empirical rule that gives us an estimate of how much of the data is between the marks. So planting your mean in the middle and going 1 standard deviation below and above the mean, in this range right here, about 68% of the data lies within those 2 values. 2 standard deviations below and above the mean, a good portion of your data, 95% of the data, lie in that range. And for 3 standard deviations below and above, almost all your data, about 99% of the data, is within those third markers. Of course, you have a little bit of values beyond that. Usually, for the normally distributed data, we draw a curve to help us get a better visual or make more sense of our data. So using our 68% here from marker 1 to marker 1 here, you can see how we have a big part of the curve. It looks like a hump or a mountain. So that's just to help visualize that a good portion of our data actually begins right here, 68%. So we are splitting this in half here to get 34 and 34 on each side of the mean. Then when we go from 2 to 2, minus 2 and plus 2 standard deviation, remember this whole amount here was about 95%. So if we take out the 68 that's in the middle here, that leaves about 27% to cut in half here to get 13.5 and 13.5. So we have this 13.5% here from these 2 markers and these 2 markers. And then from 3 to 3, from plus 3 and minus 3 standard deviation, we take that 99% and subtract out the 95 here to get 4% left over So 2% at each end, and of course we have about 1% hanging outside what we call the tails. We're going to use these percents as area under the curve to answer questions about finding how much of value lies here or there in the curve. So here is an example. We are going to be given a mean. In this case, it's hand-eye coordination test of 1,800 teenagers. The results are normally distributed, and the mean is 0.35 seconds with a standard deviation of 0.05. Because we're told that this is normally distributed, we can use the curve and the percents, which are not written there, but that's one of the first things you're going to want to do, is go through and write your percents down for each region or each interval. And then you're also going to want to put your mean value in the middle, 0.35, and then get your 3 standard deviation marks above, 3 standard deviation marks below. So with 0.35 in the middle of our curve, we're adding 0.05 above for each interval value here, and we're subtracting 0.05 here. Doesn't look like this is right here, but this is a 2.25. And now once our curve is constructed with both our percents and our data values down here on the scale, we can answer questions that say something like, what's the percent of teens that have reaction times between 0.25 and 0.40? So from here to here, they want the total percent. They want how much, see what percent of teenagers. So we're going to add up all those intervals together to get a total percent of teens with these reaction times between this value here and this value here. So 13.5 plus 68% is going to give us 81.5% of teens with between those two reaction times. The percents under the curve can also answer questions, probability questions. So here the question is, what's the probability of selecting a teen at random in that teen has a reaction time below 0.5 seconds, so below here. So finding this percent is also answering the probability question, the chances of selecting a teen and their reaction time being below. So below really means everything, all the percent except for the 0.5. So basically that's the same as saying 100 minus the 0.5%, which means 95% of teens have reaction times below 0.5 seconds. Here, it sounds like the first question we had, but it's really not. It says about how many teens, not percent, about how many teens had reaction times between 0.25 and 0.45. So we actually have a little bit more of a larger group here, 0.25 to 0.45. So we're going to take the percent, find out the total percent, and then to find how many teens, it means we're going to have to multiply that percent to 1,800 to actually find the number of teens which will answer this question. So we have 95% of the data within this range, 0.25 and 0.45 seconds. And then we're going to take 1,800 and multiply that by 0.95, because every time we're working in an equation, you always change your percent to a decimal, and that will give us about 1,710 teens that have those reaction times. The last example we'll look at today, given the 1,800 teens, about how many would you expect to have reaction times between 0.45 and 0.50. So 4.5 and 50 is 2%. So again, we are going to take our number of teens and multiply it by 0.02 to get the number of teens in this range. And so we find that there are 36 teens with hand-eye coordination within these two specified times.